Have you ever looked up at the moon and wondered, how did that get there? What we're going to do is show a simulation of what scientists think might have happened. We've got two planets. We've got the early planet Earth on the right-hand side, and on the left we have a planet called Theia, which is going to collide with the Earth. This large explosion will put enough stuff into the Earth's orbit that in the years and decades following, the moon can form from that. This is just one simulation of how the moon formed, but what I want to answer in this video is what scientists think happened and how they know. Let's take a step back. Earth's moon is big. The only other moons of a similar size are around the gas giants, but the gas giants are so large that these moons look small by comparison. Only Pluto, which isn't a planet anymore, has a similarly proportioned moon. So Earth's moon is at least a little bit unusual, being so large. So how did the Earth come to have such a large moon? To answer this, we can look at the stuff the moon is made from. We have here a graph of the oxygen 17 and oxygen 18 taken from various rocks. The blue dots here are rocks taken from the planet Earth, the black stars are rocks taken from the moon, and the red dots here are meteorites that we know came from Mars. To understand this chart, there are three types or isotopes of oxygen. There's oxygen 16, 17, and 18. All three of these are only made in stars. You can't make them in a planet. Most oxygen is oxygen 16, but around 0.2% is oxygen 18, shown on the y-axis, and a little bit less is oxygen 17, shown on the x-axis. If we look at the rocks from the Earth, they make a diagonal line. This is because there are some processes, such as condensation, evaporation, and mineralization, that distill oxygen. This concentrates the oxygen 18 and the oxygen 17 as well. But because of the fact that these processes affect the oxygens 18 and 17, they only move the rock up and down the diagonal line. They can't shift them off that diagonal line. If we look at Mars, on the though, it's below Earth's line. It's clearly offset from Earth. But if we look at the moon, it does match the Earth. It overlaps Earth's line quite nicely. When we look at other elements, the same story plays out. And this is a strong hint that the moon is actually made of the same stuff as Earth, and Mars is not. One way to explain this could be that the moon was just formed near Earth, so it started off very similar anyway, and then maybe it just got captured by Earth. But it turns out that it's actually quite difficult to get the simulations to show the capturing mechanism working properly. And this theory also isn't particularly favoured now, because it seems like too much of a coincidence, and there are a couple of other points that it doesn't explain that well either. Firstly, the moon doesn't have a very big core, as you can see here. The inner circles in blue here are the core, which is made of dense iron, and the outer part in red is the mantle, made of lighter rock, typically silicate-based rocks. Secondly, the moon seems to have less stuff with a low boiling point like zinc than the Earth does. This all paints a picture of the moon actually being made of the Earth's mantle. Something must have stripped a whole load of Earth's mantle out of the Earth, let zinc and whatever boil off, and then put the rest in the moon. The only thing we know about that could do that would be a huge collision. What astrophysicists have done is try to recreate this in simulations. The idea is to keep trying different sizes of the two planets, different spins, different angles, different speeds, and look to see if you can get results that match the real Earth and Moon. We're going to show some similar, but admittedly less accurate simulations, but I've tried to vaguely replicate the results from the literature, so we're not going to be a million miles off. In these simulations, we're running at about 450 times speed, so this means that the main part of the collision is around an hour in real life. The way that these simulations work is that you pretend the planet is made of thousands of particles, shown here by light points on the screen, each one representing about a billion tons of rock. It turns out that the first simulation here ends up with far too little moon. All the mass, a lot of the mass, which in real life would have been vaporized rock, crashes back down to the Earth, and there isn't enough left in orbit for the moon to form. If we throw the moon though at more of an angle, we can get more moon, we can get a larger moon forming. But the moon and the Earth are too different, they haven't been mixed nearly well enough. I've coloured the Earth here in yellow, and Theia in blue, so you can see how well they mix. I'm going to play one more video and let it run a little bit longer, but it's worth stressing that the point of these simulations is to see how plausible it is that giant collision could have created the moon. You could always argue, though, that if you play around with the parameters enough, of course you will get the right answer eventually, but actually the trick here is to see how difficult it is. If you find that it's very easy to find working parameters, then the theory is more plausible. But if you find that it's extremely difficult, and the parameters need to be exactly right to get this to work, then the theory is less likely to be correct. And what we find is that it's fairly easy to make a moon. It's actually fairly easy to make quite a large moon, in fact. But it's not that easy to get the planets to be well enough mixed. The way that people now think that might be solved comes from looking carefully at what happens after the collision. Remember that these are being played at 450 times speed, so they only cover a few hours. But the calculations suggest that the rock vapor would actually take decades or even centuries to cool down enough to form a solid planet. This leads to a recent idea called a Synestia, a fast-spinning planet with a vast atmosphere of rock vapor that spills out from the edge of the planet. So here's an image of a Synestia. This time it's made from somebody else's published simulation data, but I've done the rendering here. The credits at the end will give more information about that. You can see a bright inner planet peeking through in bright red, and there's a huge cloud of dust and gas surrounding this. We're not going to show it spinning, but let's orbit around it to get a better view. Now we can take a cross-section through this, and we will show the density in red. You can see the inner part of the planet still make a nice coherent blob in the middle, but the atmosphere extends tens of thousands of kilometers into space. This atmosphere of rock vapor might well be the key to the mixing problem. This Synestia would last for tens of years, maybe a century even, and that would give plenty of time for the two original planets to be very well mixed. It's only really decades, centuries later, when it starts to cool, that this would start fragmenting and separating into separate planets. So is this the whole story? We've got the collision, we've got the isotopes showing that the Earth and the Moon were properly mixed, and we've got the Synestia that explains the mixing. There's just one more part of the puzzle. How would the Synestia form the Moon? I've got a fairly inaccurate simulation here to try to illustrate this, but the truth is this hasn't been perfectly modelled by anyone yet. And that's because it's complicated. It takes a lot of computing power. But basically, if we model the cooling Synestia again with lots of particles, you can see that at the outside, further from the Earth, these particles start clumping together. The inner part is still swirling around very fast, and the inner part isn't forming clumps, but as material starts migrating out, you get these clumps, and more mass ends up in the clumps. As time goes on, over centuries, this would form just one single moon because of collisions. Now, I'm going to end here, but this is my first video, and I want to continue making these videos with a combination of explanations and simulations. And what I'd love it is if people like this, please give feedback, and above all, do click on the subscribe button if you want to hear from the next videos I make.